Okay, now let's make this slightly harder. Let's take the same problem, make it two-dimensional. Okay? So you need your 3D glasses to visualize this. Okay? Apparently 3D glasses are really good for men who are in the age range of 25 to 34, and it gives everybody else headaches. It's true, actually. So now we're going to slice up an x, slice up an y. And now, you remember those checkerboards that were so cool when you were a kid that I thought they were cool as a kid, where, have multiple levels. I think there also was like a Star Trek episode with it or something. Anyway. No, rings no bells. Anyway, if you think about it, it's like multiple levels checkerboard. This is delta t into the future here, so this is like time. Here, this is x versus y. And when we start thinking about, hey, I want to compute the solution in the future, well, what it's going to really rely on, if I look at that point down here, it's going to rely on that point and its neighbors for the derivatives. Okay? Does that make sense for everybody? So you take these points here to compute the future point for that, and then you go and compute every single future point. Okay? All right. Now this problem is getting us closer to what we want, which is we want to solve this, and the claim that I'm going to make here is that this is no different than what we just did. It's just going to result in this problem right here. Same problem. Different matrix A. And the delta here will be how we cut up delta x and delta y. I'm assuming they'll be the same. Okay? And in fact, didn't we already build that matrix A that takes two derivatives in x and two derivatives in y with periodic boundaries? We did in class. Remember when we first started playing around with SP diags? That was actually was that Wednesday? We did that? I think it was Wednesday. Wednesday we built that matrix. Right here, right there. I was right there. Where were you on Wednesday? Leah was not up there that close. She was back there. Anyway. We built that matrix A. And that matrix A really relies on us just simply figuring out how to arrange our data. Ultimately, remember, you are ultimately just a manager for this problem. Right? MATLAB's going to just go do stuff for you. You have to manage how you want to collect the data and store it. So in this case here, right, what we're trying to do is say, all right, how do I arrange my data? I want to arrange my data because that's going to be critical for this problem. And if you remember, the way we arranged the data was that the vector u that we're solving for here is the following. u11, u12, u13, all the way to un(n), and then u21, u22, u2n. Remember, we just stacked it all up to a giant vector. Vector. You seen Despicable Me? No? I'm vector. No? You guys haven't seen it, have you? My daughters are quoting from that all the time. And they love to do the little scene with the guy who's vector. He's, I'm vector! Because I have both magnitude and direction. Oh, yeah! And it's like this Bill Gates looking guy. It's hilarious. So I know you don't have any plans for this weekend, because every time I ask, it's like, nothing. There's a red box down in U Village, 99 cents. Go get your Despicable Me. It's hilarious. You love it, and it's math. Vector. Vector. There's vector. It's all about that arrangement. And by the way, we built the matrix A already. Now the question is, I want to do this in MATLAB. I want an efficient way to do this in MATLAB. So I want a code that can take this thing that I define like this and knows about two-dimensionality and knows how to make it one-dimensional. Right? I have x and I have y. I'm going to specify an initial condition on a two-dimensional grid, and I want to plot it on a two-dimensional grid, but when I go solve it, I got to put it into a vector. So here's how we're going to do it. So we're going to write a little code up here. first you would build the matrix A. We already did that. Second, now, let's just, for lack of a better term, call it setup. The setup of the problem. How are we going to set this problem up? It's two-dimensional. Okay? All right. So first of all, let's do a few things. Here's some code. Let's set up the x and y lengths. The box length in the x direction will be 20, and the y direction will be 20, right? So I'm just setting up a box, okay? And I'm going to chop these boxes up to a bunch of points. Now, what we're doing so far is doing everything's going to be chopped up the same, right? Delta x, delta y are the same. So let's do that. So let's call n of x is 100, and the y is 100. Chopped them up. So far, so good? Everybody's good? All right. Now, I'm also going to define this variable n, which is nx times ny, because actually that's the size matrix I'm going to have to work with, right? So this is going to be a 10,000 by 10,000 matrix. This is that matrix A that's going to take 2 derivatives in x, 2 derivatives in y. And we're going to be working with vectors that are size 10,000 by 1. Okay? This is how we're going to store our information. We're going to take this 100 by 100 grid, stack it up. That's what's going into MATLAB. When we get it out, we have to unstack it to plot it. Okay? So let's define our x2, which will be a linear space that goes from negative x over 2 to Lx over 2 in nx plus 1 points. Remember, part of the reason we go to nx plus 1 is because the last point's going to be the same as the first. And so the x we actually want to work with is just the first 1 through nx points. Okay? So now we decided it's going to be this big with this many points. There's our x vector. You do the same thing with y. y2 is a linear space, negative ly over 2, ly over 2, and plus 1, and y is equal to y2, 1 to ny. Okay. Now, here's a question, and this is an important one to ask. Does x know what it is? We ponder such things. Does x know it's the x direction and y know it's the y direction? Right? These are just vectors. You know what they are. And it's important that you teach MATLAB what they are. It has no sense of direction. Right? These are just things that are like, I'm a vector with 100 points. And I'm a vector with 100 points. Now what you think they are is, this is how I'm breaking up the x direction, and the y direction is orthogonal to it. And these things are two vectors that mean something in space. Okay? They form a mesh in some sense. And in fact, to think about then relating these x and y back to this picture, which is ultimately what you want to do, what you've just done with all this is you define these guys and this guy, but it doesn't know that these are directions. So I'm going to teach it that these are directions. So to do that, we do what's called the mesh grid command. So, here it is. Call them capital X, capital Y. Will be mesh grid x, y. Good? What this does is it gives things direction. It knows now that capital X and capital Y are x and y directions, orthogonal directions. Okay? Sense of direction here. Now if I work with these, I'm good. It knows what they are. By the way, these are matrices now. These are going to be, so these matrices here are n by n, or nx by ny. Okay? And it knows that This conveys all the information of where I am in the space x direction. This one conveys where I am in the y direction. And why is this important? Because we want to define an initial condition. And maybe my initial condition is just put a Gaussian in there. And you know, normally you just write down a Gaussian mathematically like, hey, here's a Gaussian in x and y. Yeah, but I better know what x and y are. If you just do this with those vectors x and y we defined, it'll give you a vector. It won't give you any kind of 2D structure. What we mean by this is something that's like a Gaussian bump. So you have to tell it that it has to know that it has these directions. And so if that's our initial condition, we can say u is equal to negative that. You use the big X, big X, big Y. And if you were to plot this, that's what you would have gotten, that thing I just erased. Okay? Now comes what we want to do, which is now that you have this, there's still one very important thing left to do. This is a matrix, and its size is nx by ny. And what we need to do is put it in that reshaped form, right? We need to stack it all, right? Well, there's a nice command that does this. Let's call this little u, and in fact, it's called reshape. You take this thing u, and you make it into a n by 1. Took this thing in 2D, dropped it down. Yeah.
The brackets. Is that the same thing?
Colon in the brackets.
Like U bracket, colon, close bracket.
Where? Colon.
For that.
Here? No, at the top on the left-hand side.
No, the reshape. Never mind, we can look at that.
Okay. Okay. So this just tells you how you want to reshape it into big n rows, 1 column. Sets up all your data. Okay? Now you have a big, giant vector, 10,000 by 1. Okay? And then you would actually use the same code. So this is pretty sweet. I didn't even plan that, but man. Or, no, I totally planned it so that by the time I got over here, I could just recycle a board. Okay? And then you just do the same thing. You just go, hey, check it out. Throw in my initial condition, which I didn't call U naught. I just called U. My matrix A, which we built already, which is that 2D thing, is 10,000 by 10,000 sparse matrix. Send in your dx, which was really delta. Fine, we'll call it dx. Boom, there you go. And then you just have the same thing. Now, let me emphasize again at this point the importance of U not forgetting to manage your T-span. Now we're in 2D. We have 10,000 points that we're solving for. 10,000 differential equations we're solving for simultaneously. And by the way, this is only 100 by 100, right? This is child's play, okay? This is not child's play if you don't get this right. Like, you know, if you do 0 to 10, they say, oh, yeah, take 10,000 steps times 10,000. The amount of data you're collecting that you're forcing MATLAB to keep for you is unbelievably large. It will crash. You will not get anything. You have to throw data away. You might say, hey, you know what, just keep every 0.5. Every slice I keep is 10,000 points. Okay? This problem is exacerbated. I can't even say that word. I shouldn't even try. But this problem's bad. It's an easier word. Okay? This problem's worse when you start thinking about, what if I go to 3D? This 10,000 by 10,000 becomes 1,000,000 by 1,000,000. So you see the problem? Scaling, PDEs, large systems. Figure out this. Make sure you manage your time. Right? If I do this, what I'm going to save is 21 slices of time. then you can plot that. That's manageable. Don't let this thing bring you out 10,000 slices of time. You'll regret it. Okay, so this is the basic structure. Now, what comes out of this thing, and this is important, is y. Y is my solution. What is y? Y has the rows of y are times 0, time 0.5, time 1, time 1.52. So there's 21 rows here. And in each row, 10,000 points. Here is my solution vector. It's 10,000. And I want to plot it. Well, you don't want to plot that. You want to get it back to 2D. So really what you'd say, suppose I wanted to plot, you might write a loop like this here. For j equals 1 to length t. And what do I want to do? I want to pull out one of the time slices, pull out one of the rows. So I could say, okay, go in here and pull out the jth row. Pull out everything in the jth row. Sorry. What I want to do with this is reshape it back. So you can say, let's reshape it back into a nx by ny. So I grab the row out, 10,000 points, and I reshape it back to a 10 by 10. Let's call that u again now. And then you could say, it's a 2D plot, so you could use something like, there's a command called pcolor. And this will show you a top view of this thing. So pcolor, u it, and then it comes back, does the next one, the next one, the next one. So just you almost see like a little movie up there. Okay, we'll play around with plotting like this. But the important thing I want you to know is that you have to reshape this if you want to start plotting it again, right? Remember, whenever you go into OD45, you're working with vectors. Even it's a fake, right? I mean, you're putting it into this just because this is how you manage your data. But you have to come back to what you really want to do, which is this has meaning. This data has meaning as a structure in 2 dimensions, 3 dimensions, and how you want to plot it. Okay? So your job as a manager of the code is to figure out where am I in the code. And if I'm going to talk to OD45, OD45 wants everything in a certain way. Put it in a certain way. But over here, what makes sense is a depiction of the dynamics in space and time, which, by the way, isn't what OD45 is giving you. OD45 is giving you this giant, massive vector out with no dimensionality until you reshape it back. And that's how you kick it with MATLAB on the OD45. We're going to do a lot more of this as we go along, but there's the warm-up of what we want to start thinking about as we start developing into homework 3 and 4. Have a great weekend. Despicable Me, 99 cents, red box. Nice. And you guys can come in and do vector. All right.